Hello, and welcome to Calm, Cool, and Collected, selecting the right sensor for your hazardous environment. I'm Jared Orzalak with Everright Position, and let's get started. In this webinar, we'll discuss what is a hazardous location, how a device is made to operate in a hazardous location, what an intrinsically safe device is, as well as an explosion-proof device, talk about some sensors that are developed for use in hazardous locations. It's important to note that the final decisions on products in a hazardous location must be made by a safety engineer who has knowledge of the location and complete hazardous location. So when we're designing for a system in a hazardous location, where do we start? It's dangerous. It can be confusing, overwhelming, or I personally like to describe it as humbling. I've been working in this application with hazardous sensors for 10 years now, and every time I really get into an application and dig in, I find myself learning something new. So it's part of that is due to just how broad the systems and regulations are, and part of that's due to the fact that this is an evolving market. So it's just something to keep in mind as we go through. What is a hazardous location? So a hazardous area exists where a potentially explosive mix of air and flammable gases, or air and dust, or air, dust, and gases may occur. Really, this is getting back to chemistry 101. To cause a reaction, you're going to need fuel, oxygen, and an ignition source. And only when those three things are available and in sufficient quantities are you going to get a reaction, or specifically, in this case, an explosion. One of the challenges is there are so many potential ignition sources. Everything from open flames, lightning strikes, impacts, static electricity, and high surface temperatures could all be potential ignition sources. Hazardous locations are rather common. Could be anything such as a chemical refinery, fuel station, paint booth, mining, agriculture. This often gets overlooked by folks. You have grain mills, sugar refineries, silos. All these can have a significant presence of combustible dust. Printing industries, paper, textiles, sewage treatment plants, garbage refuse facilities. If you drive by those, you'll often see gas being burned so that it can accumulate and explode. But the list goes on. It's rather extensive. Before getting into the details on this slide, the most important takeaway is just the simple fact that not all hazardous locations are created equal. Some will have a continuous presence of an explosive atmosphere. Others, it will only be for a short period of time and only in abnormal circumstances. So that's really what we're trying to take away here, is that first thing to do is defining which zone or classification you would be in. In this specific slide, we're using the zone system where we have zone 0, 1, and 2. Zone 0 being where the explosive atmosphere is continuously present over long periods of time, whereas zone 2 would be where the explosive atmosphere wouldn't occur under normal operation. And if it does occur, it will be for only a short period of time. Zone 1 being somewhere in the middle. So specifically in this example, zone 1 is where you have fuel passing through a hose, going from one container to another. One approach to creating devices for use in a hazardous environment is referred to as an intrinsically safe device. And the logic is, if you can't remove the fuel, remove the ignition source. And specifically how an intrinsically safe device accomplishes this is it's incapable of releasing sufficient electrical or thermal energy, or under normal or abnormal conditions, to cause an ignition of a specific hazardous atmosphere. And in layman's terms, how that's accomplished is an intrinsically safe device limits the amount of power that can be present in the hazardous location. So most commonly, we'll have an intrinsically safe barrier, which will be wired in series with the device. The barrier is located in the safe zone, which is outside of the explosive area. And the barrier is going to limit that power that's going to be passing through to the sensor. Typically, it's going to use a Zener diode to limit the voltage. You might have resistors to limit current, a fuse, and the temperature of the device still needs to be considered. So make sure that that can't cause the ignition. At the other extreme are devices that are referred to as non-sparking. And how that device is developed is it's made to prevent sparks or excess temperatures under normal circumstances. It's designed for less stringent environments, and the explosive atmosphere is not usually present. That may sound similar to the intrinsically safe description, but the biggest thing here to note is the intrinsically safe sensor will not cause an explosion under normal or abnormal circumstances. The non-sparking device, however, is being specified to not cause a spark only under normal circumstances. So basically, here's your sensor. There will not cause an ignition source inside when the sensor is used under normal circumstances. There's also devices called Flameproof. These are devices where a hazardous atmosphere, even if it gets within the enclosure and does get ignited within the enclosure, the housing or enclosure of the sensor will contain the explosion. For the flame-proof devices, let's look at in a little more detail how that device accomplishes its safety in a hazardous location. So these explosion-proof devices are created such that if an explosive atmosphere penetrates into the enclosure and a trigger produces, the explosion occurs, but it remains confined in the enclosure, as stated on the previous slide. Now, again, that's easier said than done because you need to make sure that the spread of the flame does not occur to the surrounding atmosphere and that the external temperature of the housing will not get so hot that it could ignite vapors in the area. So a lot of thought needs to go into the mechanical construction of one of these enclosures. And that's accomplished by looking at the mechanical strength to contain the overpressure of an explosion, and then also the addition of a flame path for the escape of the flue gases. And this allows the gases to exit the enclosure and to cool down during the process so that when they do exit, they're no longer hot enough to trigger an explosion in the outside atmosphere. Visually here are a couple examples of different flame paths for the gases to escape. It's important to note that these devices do not use an intrinsically safe barrier, such as that of the intrinsically safe devices. One of the advantages is these devices, since they're using typically common, or if not the same, electronics as traditional off-the-shelf devices, is that analogous devices are available usually at a significantly lower cost that could be used at different parts of the system that perhaps are not in a hazardous location. So this can help to reduce your cost and overall system complexity when developing a full system at a given location. With respect to regulatory requirements, it's important to think about not only where you're currently located, but where your products may be located. Certainly, it's not uncommon for products in North America to find use in Europe and Asia, and vice versa. Fortunately, many of the devices that are made for use in one area have analogous products that are made for use in other areas. But it does increase some complexity, and again, this is where you're going to want to refer to your safety engineer for advice on when different products may be needed. The labeling can be different. Here's some examples of North American and European labeling. One of the things specifically you'll notice is the use of division system and the use of a zone system. Here's a little more detail on the class diff versus the zone system. One of the things that's important is, again, sometimes a device that is rated and qualified in North America may be appropriate in Europe and vice versa. Other times it won't. Generally, the more stringent an area is, for example, if it's zone 0, they're going to be more stringent about having devices that are approved in other geographical areas used. Last, a little more on class and diverse zone. So in the US and Canada, they've recently revised installation codes to recognize the ATEX or International 3-Zone area for classification. In Canada, new installations must use the 3-zone system, and in the US, you can use either. So while this adds some flexibility, it also adds some complexity. Just something to be aware of. For the second half of this presentation, I'd like to change our focus here and look at some of the sensors that are currently available on the market for use in hazardous environments. Specifically, we'll be talking about rotary, tilt, and linear, but there's a broad variety of other sensors such as temperature and pressure that are also available for these types of hazardous locations. The first products we're going to talk about are those from Posital. Posital was founded in Germany in 1918, but has had a significant growing global presence in the last 20 years. The focus of their products are explosion-proof devices looking at eliminating the active ignition source. Posital products include rotary encoders and inclinometers. There's a very large variety of products that are made for explosive environments. There's a universal compact mechanical design that all of these sensors have in common. There's no different electronics. So that allows for easy application installation since we're using the same interfaces as used on their other products. And it also creates support for a wide variety of different interface options. The products are developed with a global view and a focus on regional explosion-proof certification. One product that Posital has for explosive environments is what they refer to as a non-sparking type. And this is a design that prevents sparking or excess temperatures, as previously discussed. And how this is accomplished is through the use of special seals, glands, and it's produced only by trained workers. These are dedicated for Zone 2 and 22 and Div 2 Class 1. You can see the certification here. There's a manufacturer self-declaration for ATEX. Their Profinet encoder already has a UL Div 2 Class 1, and in the future there will be additional certification for these products. For more hazardous environments such as Zone 1 and 21 in underground mining, Posital offers a flameproof enclosure. And this is an enclosure where the explosion occurring inside the encoder won't propagate to the outside environment, as we previously discussed. In addition, these will have certification for use in China coming up as well. Posital's ATEX inclinometers take a different approach. Here we're using an encapsulation to isolate the electronics from the potentially explosive atmosphere. These are rated for Zone 1 and 21 as well as underground mining. In summary, Posital makes rotary encoders and inclinometers for ATEX, ICEX, and UL certifications. There's a wide variety of interfaces available. There's no battery backup. This is really important to emphasize, as that battery could be a potential ignition source due to it storing energy. They're very flexible as far as how you connect these sensors, whether it's through a connection cap or a cable exit. Different certification levels for different applications. High resolution. We also offer programmable incremental encoders and stainless steel housings. The other company I want to introduce today is Positec. They were founded in the UK in 1992. They're part of the global Variome Discovery group of sensor companies, and their focus on hazardous location products is on making them intrinsically safe. Positec's main product area are linear sensors, but they also do rotary encoders and inclinometers. There's a large variety of explosion-proof products and very short lead times, especially for this industry. 4 weeks is standard and 1 week is expedited production. All Positec hazardous location products rely on the use of a galvanically isolated amplifier barrier, which should be located in a safe area. And what this barrier does is it limits the electrical and thermal energy that could go into the hazardous area. Fundamentally, it's a half to 4.5 volt output ratiometric circuit, and the barrier can output a voltage or a current signal to a PLC or display based on what the specific application needs. It's important to note there's an optional 5-wire installation between the barrier and sensor. What this does is it negates the effects of the loss over the wires and any thermal effects. And as a result, you can have up to 1 kilometer between the barrier and the sensor. So for a very large hazardous location area, this is really appealing for users. Here's kind of an overview of all the different series options from Positec. So you can see they have sensors for gas, dust, and mining. Lots of different applications that these sensors could be used in based on whether you're looking at linear, rotary, or tilt positioning. Positec offers a wide variety of different mechanical form factors. Here's just an example of some of the different linear options that are available to fit different physical restraints, or some are made to be more robust than others. At this point, I want to say thank you for joining us for this webinar. Special thanks to Wojtek Pajak of Posital and Mike Spreadbury of Positec for their information and help with this presentation. Unfortunately, we weren't able to include them in this re-recording. For any questions, please feel free to contact myself, Jared Orzlak at Everright Position. We'd love to hear from you, learn more about your application, and see how we can help. Take care.